Hello, good evening. Today is December 6th and it's around 8:40 p.m. Dallas time, which is United States Central Standard Time. And I'm Bhavani from the University of Texas at Dallas. And I'm recording this video presentation, which is going to be given as a keynote presentation at the IEEE ACM Conference on BDCAT, Big Data Computing Applications and Technologies. The conference was supposed to have been held in Leicester in the United Kingdom, England. But because of COVID, it's now a virtual conference. So I'm recording this as a placeholder presentation, just in case there's a technology glitch. But my actual keynote presentation is going to be on Wednesday, December 9th, 2020. And that will be at 8:30 a.m. United States Central Standard Time. And that will be, I believe, around 2:30 Greenwich Mean Time, which is also the British Standard Time. Okay, so I'm going to share my screen, and my talk is going to be on integrating cybersecurity and big data / data science / machine learning AI, and talk about what are some of the challenges and some of the opportunities. And then I will discuss one application, which is the Internet of Transportation and Infrastructures. Okay, so I'm going to share my screen. Great. Okay. So integrating cybersecurity and data science / artificial intelligence, which is also big data with applications in Internet of Transportation and infrastructures. Okay, so there's 3 parts to this presentation. Part 1 is going to be integrating cybersecurity with data science AI, and I call it SEC AI. In particular, I'll talk about big data security and privacy. It's something a workshop that I organized about 6 years ago for the National Science Foundation. And since there have been numerous developments in this area. So a brief overview of big data security and privacy, and then talk about privacy aware quantified self, and then data science for cybersecurity and securing the data science machine learning techniques, right? So that's part 1. Part 2 does not talk anything about AI. It's just about a particular example of a cyber physical system, which is Internet of Transportation and Infrastructures, and looking at security and privacy. It's the work of one of my PhD students. Then part 3 is the future. It's going to talk about applying part 1, the results in part 1, to the results in part 2. And the acknowledgements, number of our sponsors, and also my colleagues, Professor Alvaro Cardenas, Professors Alvaro Cardenas, so Alvaro Cardenas is an expert in cyber physical system and security. Murad Kantajlu is an expert in privacy and securing data science. Professor Latif Khan is an expert in data science for cybersecurity, and our former PhD students, together with Professor Cardenas and myself, Dr. Raul Quinones, and so he did much of the work for part 2. And then our project coordinator, Ms. Rhonda Walls, who organizes all our efforts for Cybersecurity Research and Education Institute. So SEC AI, integrating cybersecurity and AI ML data science. So what is our motivation? The motivation is something that happened the late 1990s, early 2000s, data mining, security and privacy. So before we had data science, and after data management, data mining in the 1990s. So I talked about data mining and the security and privacy aspects due to data mining. And I presented a keynote address first at the IFIP 11.3 conference in data and application security in 1996 in Como, Italy. And then the Pacific Asia Knowledge Discovery Conference in 1998 in Melbourne, Australia. And published, I call it a landmark paper. Why? Because I was a program director at NSF. And I published a paper that sort of spawned a new area of research. Okay, so then around 2000, IBM researchers in Almaden Research Center, they were working on privacy preserving data mining. So their idea was to take the original data. So you don't want to divulge the original data because original data will have information such as, our healthcare records and various other sensitive information. So you add noise and then you have a modified data mining process, but the end result should be the same. Otherwise, what's the point in doing data mining, right? So this is privacy preserving or privacy aware data mining. And then when I joined the University of Texas, Dallas, so by the way, the early keynote addresses were when I was with the MITRE Corporation, the Federal Research Lab. And then when I joined the University of Texas, Dallas, I had my first PhD students jointly with co-supervised with Professor Murat Kantajulu, Dr. Li Liu. She focused on privacy preserving data mining and in particular, the perturbation method and also privacy preserving decision trees. And that was between 2005 and 2008. And data mining security and privacy is exacerbated now with big data, right? Because lots and lots of data being collected and this data is being analyzed. And of course, data science, AI, machine learning. So there is so much capability now to analyze lots of data, right? So we hosted a National Science Foundation workshop on big data security and privacy in September 2014 and presented the results to the interagency working group. That's with all the government agencies in February 2015. And as a result of that, there were a lot of programs that got started at various agencies on data privacy. So what is this big data security and privacy? So due to all these technological advances and novel applications, it is possible to capture, process, analyze lots of data, right? It's for healthcare, for finance, for retail, you name it, right? There is big data applications, data analytics. Even for cybersecurity, right? You need data analytics to figure out who the bad guys, the bad malware, right? So these tasks could be authentication, access control, anomaly detection, user monitoring, insider threat and analysis, and so on. By analyzing and integrating data collected on the web, we can identify connections and relationships among individuals. That could in turn help with homeland protection, disease outbreaks, and so on. Collected data, even if we anonymize, like we can remove identifiers, but you can put records, different records together and infer something that is highly sensitive or highly private. So security tasks such as authentication needs a lot of data, detailed information about users, multi-factor authentication. So when you look at biometrics, you need fingerprinting and facial recognition, facial features, all of that has to be collected. So this information misuse or stolen can lead to privacy breaches. And so we talked about two directions: securing the data, access control models, and privacy enhanced techniques, big data analytics for cybersecurity. A third area that we really didn't focus, but we were doing some work, and that is also at the workshop, we didn't focus on that, but that's become one of the most important areas now in cybersecurity. And what happens if the machine learning techniques are attacked, right? So then you cannot depend on the results, right? Because you are using machine learning techniques for a number of applications, right? Healthcare, cybersecurity, finance. And so if these machine learning techniques are attacked, it will say, instead of by Microsoft, it's going to say by Google, right? So that's going to be disastrous. Okay, so that's the whole idea. Okay, so we came up with some of the directions. So after that, we did some work on privacy-aware quantified self. What is quantified self? Quantified self is a movement by psychologists and sociologists to gather lots of information about people so that you can give advice. For instance, if I open my refrigerator and if I start eating my chocolates or getting my chocolates out, the system would say, no, you are not supposed to eat chocolates or vanilla ice cream, my two favorites. It's bad for you. So that's going to be very good for my health. But imagine the system has collected all this information about me, so my privacy is going to be violated. So that's what we are saying here, right? Quantified cell movement, a lot of personal data collected from wearable devices, which could be your Fitbits and your blood pressure monitoring and your blood sugar monitoring and so on. Such detailed data, right, you've got to share with various organizations in order to give advice to you. But like the glucose levels, this information could be used to deny insurance coverage. You could be a diabetic. Your children then could have potential to have diabetes. So such privacy violations could easily get out of hand or out of control. If data collectors could aggregate financial health data, lots of information, Facebook activity, purchase patterns, and so on, and there could be so many lawsuits. So to address this growing challenge, we need tools for these quantified self applications to ensure privacy. So what did we do? So we've come up with a privacy-aware quantified self. It's all based on policies. So here we have the health information, fitness data, location, social media, image, and so on. All of the data is collected. Data collection, storage, analytics, sharing. And some of the encrypted backup data goes into the cloud storage, cloud-based services, anonymized data, encrypted shared data, query results. And now you have privacy-aware quantified self-manager running on a mobile device. Okay, so this is the mobile device. And here you have the data collection, storage, analytics, and sharing. Every action, every task has to be policy-driven. Policies have to drive data collection, data storage, data analytics, data sharing. Okay, so that's the whole idea. So what does it mean? So policy-aware data collection. So as more data collected and storage on the device will not be sufficient, right? We envisage there could be encrypted cloud storage. So policies have to specify what data should be in the cloud storage, what should be in the mobile apps. And then based on the access control policies, you can say local apps running on the device could be granted access. When needed, these apps will be allowed to access some of the encrypted data. So all of that guided by policies. In some cases, you may not need to have fine-grained collection, right? You may see if a person is 20 years old, you may not need to take the blood pressure or the glucose levels or even the weight. But if you're 70 years old, it's different. In other cases, the data may have to be deleted to preserve privacy. And what happens when the data is deleted? Is it completely gone? So what are the delete policies? And then we envision that data sharing and analytics will be carried out using the services running in the cloud. And then based on different scenarios, some data could be sent without any modification, heart rate, and so on. Some could be sent without, with some sanitization and so on. Okay, so policies have to guide this entire process. Okay, so that's the one part, policy-aware, privacy-based, privacy-aware, policy-based data framework. The next topic on integrating AI and cybersecurity and data science is with respect to intrusion detection, insider threat detection, and so on. And so we've done a lot of work on stream classification. My colleague, Professor Latif Khan, together with Professor J.W. Han from University of Illinois, Urbana-Champaign, we've done a lot of work. And so what we do here is data streams, right? We use past data to build classification model, predict the labels of future instances using the model, and helps in decision making. But data streams, big data streams, continuous flow of data. So very common for network traffic, for financial data, so massive amounts of data. But what happens is that the concepts could change. So today could be by Microsoft, tomorrow could be by Facebook, the day after it could be by Apple, the next day it could be by Amazon, and then by Google. So concepts are changing. So that means one model is not going to fit everything. So what do? You build an ensemble of models, and then some of the older models where the concepts are old, they are thrown away and replaced by new models. And they do some voting here, right? And then you have the attack traffic. If it's attack, when the test data comes, if it's attack, then you block and quarantine. Otherwise, benign traffic, you store in a server, and then some expert inputs can do the help with the model update. And so this is our algorithm for our approach for changing concepts, concepts that are changing, and also for continuous data streams. How do you analyze continuous data streams? So ensemble of models that are continuously updated, right? So you can think of it as real-time modeling. Okay, so we applied it to insider threat detection. Insider threat requires identification of rare anomalies in contexts where evolving behaviors tend to mask such anomalies. We have designed and developed ensemble-based stream mining. That's what I was mentioning earlier. My next chart is going to show some more details. We have used both supervised, traditional support vector machine, and one-class support vector machine. And for unsupervised, we use graph-based anomaly detection. And we have papers describing all of our techniques, right? So unsupervised, we also use some compression because lots of data being collected, so for more efficiency. So we have developed classifiers with tremendous accuracy, and the ensemble of classifiers allows the unsupervised or even supervised to outperform traditional static approaches. Anyway, so here is our approach. So you have system logs, and so you look at the series of calls, okay? So you have ki chunks or I chunks, and then you are building an ensemble of models, feature extraction, and you do learning with graph-based for unsupervised, and support vector machine or one-class support vector machine, ensemble of models, and these models are continuously getting updated. And then when the I+1 test data comes in, extract the features and do the testing, and is it an anomaly? So the important aspect of our approach is this ensemble of models that are continuously being updated as the concepts are changing. Okay, so we applied that and we got some very useful results. Okay, the next topic is securing data science, AI, machine learning. And so this is the, as I said, one of the most important topics, which is adversarial machine learning. The adversary modifies data to defeat learning algorithms. And we have to understand the adversary. It's not about concept drift. It's not online learning. Adversary adapts to avoid being detected during training time, data poisoning during testing time, modifying the features when data mining is deployed. So there's a game being played between us and the adversary. So I'll tell you. So the red here, this is the support vector machine boundary. The red squares are the bad instances, and the blue squares are the good instances. Blue circles are the good instances. And so what happens is that adversary is learning what's the data we are using, what are our models. Once it has figured out, it's going to try and push the bad instances into the good instances, and it won't be detected. That's a challenge. So we have to now figure out what the adversary is up to, and we've got to modify our behavior. In the end, it becomes gameplay. So before we do anything, we have to figure out what the attacks are. So we looked at two types of attacks. One is a free range attack, and the other is a targeted attack. And our attack and our paper, all our work is described in our KDD paper. That is the ACM Knowledge Discovery and Database Conference. And so free range attack, adversary can move malicious data anywhere in the domain. That's what happens here. And so anyway, I won't go into these details, but the paper explains very clearly what the aspects are and what are the types of attacks. Okay, so only two classes of attacks is what we have looked at. In reality, there could be many more attacks. Okay, so what do? We study the attacks, right? And then this is a support vector machine boundary. And red crosses here are the bad instances and the green circles are the good instances. We are going to try and push the boundary to this blue line. And it's not easy. Okay, I'll come to that. So by pushing it, some of the bad instances which would not have been caught are now getting caught. So if you look at here, we have pushed it and all of these bad instances, this black stuff here, the black crosses or circles, I mean crosses, whatever, they are being caught. Now you can ask the question, why not move this right here? So all the instances, because some instances are being missed. If we move it right here, all the green circles here are going to be detected as bad instances while they are really good. So we are going to get some false positives. So we don't want false positives. We don't want false negatives either. So what do? Looking at the attacks, and we will, with a lot of mathematical computation, we come up with the ideal position for this blue line. So black dashed line is a standard support vector machine classification boundary, and the blue line is the adversarial support vector machine classification boundary. Okay, so the threat model, as I said, attacker can modify test time, deployment time, x to x prime, modify packet length. It can add dummy bytes, add good word to spam email, and add noise to an image. Okay, so this was our work, and we got some very interesting results. So this finishes part 1. Now, part 2 is on security and privacy for Internet of Transportation and critical infrastructures. Okay, so my first part was joint work with my colleagues, Professor Murad Kantajulu and Professor Latifa Khan. This work is with my colleague, Professor Alvaro Cardenas, but all of the work is with students. Okay, so we have many students. So this particular work is with Dr. Raul Quinones. The earlier work, of course, we had multiple students for the data science, integrating cybersecurity and data science. Okay. Internet of Things, we know that, right? Our refrigerators connected to our cell phones, connected to us, our televisions, to our lights, and then to our cars and so on. Then there's medical Internet of Things, there's financial Internet of Things, but we are talking about Internet of Transportation, right? So the cars are all connected, cars connected to trains, trucks are connected, and they are all connected to the roadwork. So everybody is informed as to what is going on in order to have more efficiency in driving, reduce accidents, and so on. That's the main goal. Okay, that's Internet of Transportation. So IoT, Internet of Transportation, major implications in the transportation. Autonomous vehicles aim at improving day-to-day activities, such as delivering packages, improving traffic, and the transportation of goods. In the US, trucks carry a lot of freight of goods, like 63.3%. AVs, the autonomous vehicles, are not limited to ground vehicles. They also include aerial, sea, like drones and airplanes and ships and boats and so on. Wide range of applications. Levels of automation for AVs range from 0 to 5, with current ground vehicles in the market having partial automation at level 2 and aerial vehicles having high automation at level 4. Companies are invested heavily in AVs. GM spent $728 million in R&D in 2018, with plans of increasing to $1 billion. I haven't kept in touch as to what they actually spent. It'll be nice to get the 2019 figures, as well as 2020 should be released pretty soon. While there is great potential, right, in the AVs and the improvements it can do to the transportation industry, security and privacy concerns pose new challenges that need to be addressed as we move forward. Okay, so security of autonomous vehicles. AVs evaluate their environment using a variety of sensors, camera, GPS, inertial measurement units, LiDAR, radar, and so on. Prior research has shown sensors are susceptible to malicious tampering, such as the inertial measurement units could be susceptible to sound waves, and GPS receptors are susceptible to spoofing signals. Vehicles should verify the veracity of sensor signals before acting. So sensor-based, right? We have AVs rely on sensors to evaluate and interact with their environment. Then you have inherited issues. Sensors are susceptible, as we said, GPS spoofing, transduction attacks that manipulate environment, physical signals, visual, sound, magnetic, and so on. and then needed defenses. What do you need? Classical computing security, memory protection, cryptography, and authentication does not protect, because these are physics-based systems, right? So, and no verification. Due to the real-time constraints, AVs trust and act upon sensor data without any form of verification. And that's, we need some form of verification. And that's our algorithm, physics-based anomaly detection. So we have developed a reference monitor using physics-based anomaly detection called PBAD, right, for both ground and aerial vehicles. We didn't do it for sea, right, because we don't have any oceans or, well, there are lakes, but we don't have ships and submarines and so on. I don't think so, that we have them in Dallas, Texas. The algorithm will consist of 3 parts: building a model offline, using the physical properties, AV invariance, implementing an online tool to monitor accepted observed behavior to detect anomalies. That's our online verification. And of course, if there is a problem, if it will raise an alarm, if significant residual difference exists between executions. Okay, so what is we presented in the Usenix conference. It's a top cybersecurity conference. So offline pre-processing, the AVs invariance. So this is the model, right? I'm not going to go into the models. You can see all of the values such as mass of vehicles and moments of inertia, thrust factor, drag factor, and so on. So we build this model, and then offline pre-processing, the autonomous vehicles invariants are calculated, and using a well-known nonlinear models for aerial and ground vehicles, accelerometer, gyroscope, and magnetometer sensor data on the X, Y, and Z axis is used for the aerial vehicle. Vehicle positioning and steering angle is used for the ground vehicle. Online stage, we are using extended Kalman filter. Okay, and that has been used in the electrical engineering control systems field for a long time. Is used to predict AV's physical behavior by estimating unknown parameters from noisy sensor input. The algorithm is divided into 2 sections that predicts and corrects the estimation before it is compared against the sensor data. Anomaly detection, a CUSUM algorithm is then used to detect the persistent attacks. An alarm is raised if the residual difference is larger than a predefined threshold. So this is our detailed design. What about the implementation? That was sort of fun part for the students. They were sort of working with all these gadgets and all these vehicles and so on. So for aerial, we use drones, of course, not airplanes. Intel ready to fly drone controller, PX4 flight controller, focused on detecting of GPS spoofing and gyroscope attacks. GPS attacks are detected after 0.2 seconds, while gyroscope attacks are detected after 1.5 seconds. Overhead introduced is 5.4%. Ground AV, custom built on top of Traxxas Ford Fiesta, Rally Chassis controller, ROS kinetic cam, focused on detecting visual attacks, that's here. On the camera, attacks detected after 0.1 seconds, overhead is less, 2.25. Each threshold produces a probability of false alarms of approximately 2%. So this is the physical implementation of both security for, anomaly detection for aerial vehicles and for ground vehicles. Okay, now what about privacy? Right? Beyond the security and individual vehicles, the transportation sector could greatly benefit from a supporting infrastructure that allows communication between vehicles, motion sensors on lampposts, surveillance cameras, to name a few, to help identify traffic jams and reroute vehicles to increase vehicle safety. The point is this, because see, I don't want people to know where I am. Or I may be smoking in my car. Well, by the way, I do not smoke. I've never smoked even a single cigarette, but just assume that I smoke, and I don't want people to find out, right? So I need to have my privacy while all this information is being collected, and that's very challenging. From the user's perspective, privacy concerns arise from all the information needed by such system that could lead to private information being exposed, such as vehicle identification and driving patterns. Legislatures, engineers, and scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. This will aid at improving the public perception, reduce hesitation from consumers, and increase the adoption rate of new technologies. Okay, so that's our part 2. Part 3 is how do we apply part 1 to part 2 to get more intelligent or AI-based or data science-based Internet of Transportation and Infrastructures. So data science AI for transportation security. So remember, in our security anomaly detection, we used just the Internet of, just a second, I just want to check my time. By the way, I will be present on, I am planning to be present on Wednesdays. So anyway, so data science, right. So we use Kalman filters, remember? How can we incorporate machine learning into our algorithm? So Internet of Transportation systems are subject to attack. Streaming data is being collected from such systems, including autonomous and in future driverless vehicles. So lots of streaming data coming in. And as transportation systems go electric, we need to conserve energy. And with these threats, right, we could have massive damage, accidents, loss, and so on, but we could also get stranded in lonely highways. So because of energy management issues. So data science ML techniques are being applied to analyze data. So my question is, can stream analytics, a lot of the work that we did for stream, which I mentioned earlier in part 1, can we apply them? Because we have applied them for financial and telecom data. Can we apply them to transportation data? The main question is to understand the nature of the complex transportation data and adapt the stream analytics techniques and apply them on the massive amounts of heterogeneous sensor data being collected. Okay, so that's data science for Internet of Transportation. What about adversarial machine learning, right? What happens if the data science techniques are attacked? Okay, so Internet of Transportation is going to rely heavily on data science, AI, ML, for not just cybersecurity, for a number of applications, optimum directions, driving without a human in the loop. The adversary will be learning the models used by the vehicles as well as learn about the data used in the training of the models. Adversary will attempt to thwart the vehicle's learning process. Therefore, the learning algorithms have to adapt to thwart the adversary's actions, right? So eventually, as we said earlier, it becomes game playing between the adversary and the vehicle's machine learning algorithms, right? So challenge, what sort of game will be played? Zero sum, Bayesian, Stackelberg. So we need to understand the data. That's important, right? Need to understand data is essential. Research on this topic is only beginning. Although there's a lot of work on adversarial machine learning, how do we apply to cyber physical systems in general and Internet of Transportation systems in particular? Okay, so when we talk, as I said, machine learning can be applied not just for cybersecurity, for even Internet of Transportation, machine learning for everything. What are the best directions? How can we avoid collisions, optimum driving, and so on, right? And imagine when we have driverless cars, right? That's going to be really, it could become very chaotic with cybersecurity problems. Okay, now we talk about privacy. Right, this is the future. See, I talked about collecting all the data in our smartphones for healthcare purposes, but now we are looking at radar, GPS, cameras, LIDAR, ultrasonic sensors, and in the car there is some sensor-based equipment, kind of an embedded sort of system, you can think of it, for data collection, data storage, data analytics, and so on, data sharing. And some of the data is in the cloud, some others cloud-based services. So we are developing, well, we haven't really, but we are developing privacy-aware policy-based data management framework. But what I'm proposing is a privacy-aware policy-based data management framework for Internet of Transportation. So policies have to guide the data collection, data storage, data analytics, data sharing for privacy. So again, instead of the smartphone, we have now a vehicle. Okay, and all of the data, instead of healthcare data, we have got radar data. Instead of social media, we have cameras. Okay, so that's the whole idea. Now, there's another area that we are focusing, and that is, what about trustworthy analytics, right? So computations over big data may require massive computational resources. So we're talking about machine learning and conducting analytics. So organizations may want to use a third party to do all the analytics for them, okay, outsource for all these computations. When a third party server is used, you have to assume that the environment is not trustworthy, right? So we have to assume that the environment could be attacked. And there are adversaries. There could be inside a threat in the third-party location where computation is performed. In these cases, data owners may need to protect their data and require cryptographic guarantees about data security and integrity of computational output from these third-party services. Okay, so data owners have to protect their data. So what do? So we are conducting research in secure encrypted data stream processing using trustworthy and untrustworthy analytics, and we are using advancements in embedded hardware technology, SGX, to support trusted execution environments. But we need to explore this for Internet of Transportation. But although we've done a lot of work on SGX, more recently there are some articles too. Is it completely secure? So we need to look into that more. Okay. So this is what the Intel's SGX looks like, right? You have got the users, you've got the application memory, you have the SGX library, the wrappers and the encrypted code, and then data analytics is being carried out on the SGX's enclave memory, so it can be quite secure. And so this is really what happens for the trustworthy analytics. So you can, if everything works according to plan, right, according to the specifications, then yes, it's providing security. But again, you don't know, anything could happen. I'll give you a good example for this. Okay, so let me finish this first. Summary and directions: developments in AI, integrating cybersecurity, AI, data science exploding. Applications of AI for security inside a threat and security for AI, adversarial machine learning. Also developments in privacy-aware healthcare, managing one's life's activities, privacy-aware quantified self. At the same time, with the development of the Internet of Things, including Internet of Transportation systems and infrastructures, security and privacy solutions are being developed, mainly physics-based solutions. As driverless cars become a reality, more and more of the AVs will use AI/ML techniques. How can we develop AI solutions for detecting malware in AV systems, and how can adversarial machine learning work in AV systems? How can we develop, so the question is, can we develop a privacy-aware policy-based data management framework for Internet of Transportation and infrastructures? And finally, is it possible to perform trustworthy analytics efficiently when so much data is coming from all directions? Numerous opportunities for substantial research. And I'd like to thank all my colleagues and our former student, Dr. Raul Quinones, Ms. Rhonda Walls. Okay, so I just want to say something else. Okay, so I want to stop sharing now. Okay, so what I wanted to say was, right, I said everything works according to plan, right? So what I said was, we had all these trustworthy analytics, Intel's SGX chips, and so if it all works according to plan, then great, but something could happen. When AES 256-bit encryption was developed, I believe that was about 20 years ago. Don't quote me on that, but I think around 20 years ago, we thought, who is going to break this? Because it was going to take probably millions of years for the most sophisticated computers at that time to break AES 256. But fast forward 20 years, right now, 20 years later, we have quantum computing. And quantum computers, if it all works, they are error prone at the moment because remember, each qubit, right? You can take a 0 and 1, not 0 or 1, and it can straddle, but it has the computation set. I'm not a quantum computing expert, by the way, but I've read a little bit and I taught in my big data class, like for the future, quantum computing, big data, and cybersecurity. And so I said, right, so quantum computing, I'm talking because I got a few more minutes, right? I've only talked for about 40 minutes, so I'll talk for about five more minutes, and then we'll have questions. So anyway, so quantum computing, they're saying, if we talk, okay, and you've got to do all this computing in deep space temperatures, which is very, 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 very cold, right? So as a result, even slight perturbation, slight disturbance could produce erroneous results. And so, okay, so what happens is that if it works, then they are saying that not 256, I think next is 512, 124, 2024 or 2048. 2048 bits could be decrypted, right? Could be the quantum computers can break the code within milliseconds or seconds, right? And it's going to take trillions of years for the most sophisticated computers to break, right? So how are we going to get security if the quantum computer can break 2048? Should we then go to what's the next one? 5096, and what's the next one, right? So eventually they are going to break. So then there are other researchers who have developed quantum cryptography, which is because currently our quantum algorithms are based on mathematics, right? Number theory and so on. So they are based on physics, which is the smallest of particles, is subatomic computations, qubits. So the whole idea here is to develop the crypto system based on physics, photons, and so on. But then, so they said those systems could be harder to break. But then there are articles now saying that quantum computing can break those codes as well. And so there are some other types of cryptographic methods like lattice-based solutions. So what I'm really worried is if this quantum, on the one hand, we want quantum computing for AI, big data, right? So BDCAT, this conference, big data, computing, applications and technologies, yes, right? Quantum computing is something that's going to help big data, AI algorithms in a huge way. But it's also going to be disaster for security. So otherwise there's not going to be any security. The only thing is that not everyone has access to quantum computing, because you've got to, compute it in the most strenuous circumstances, right? Deep freeze temperatures. So not everyone can afford, but there are nations, rich nations can afford to have quantum computing, and then everybody is going to break each other's systems. And that's going to be a total disaster. If we are talking about things like, people interfering in various elections, and they are breaking into, sensitive computers that various countries have, if we're talking about that now, wait till we have quantum computing. So hopefully the security researchers, and those are going to be many of the students who are here at this conference, as well as data science researchers, quantum computing researchers, could come up with viable solutions, not just for quantum computing, for AI and big data, also quantum security solutions, so that the quantum computers will not be able to break the code. So in summary, there are so many opportunities that we have for the future. And I'm so excited for all the opportunities, especially all of the students who are listening to this presentation. I'm just so sort of hopeful for you, because you all will be able to tackle some very important and challenging problems. And thank you very much for inviting me, to the conference organizers, for inviting me to give this keynote address. And again, I had my email address in one of the charts, so please email me if you have any questions. And as I said, I'm planning to be present at the conference. And so I'll be giving this talk live, but if there is a technology glitch, then I will also call in by phone, and then I'll be able to answer the questions. So they will play the presentation, and then I'll be able to answer the questions, right? So either way, I will see you on Wednesday, December 9th, 2020. Thank you. Bye. And I'm going to stop recording now.